Hey everyone, Morgan here. So this is it. This is our last unit of the year, the one on organic chemistry. And we're on page 1 of that outline. So simply put, organic chemistry is the study of carbon-based compounds. Now, all organic compounds will most definitely have a carbon in them, but they will have lots of other stuff in there also. Hydrogens for sure, and then lots of oxygens and chlorines and nitrogens and other stuff will pop up, okay? Now, we generally credit a German named Friedrich Wöhler, with the first organic synthesis, where he took things that were inorganic and synthesized urea out of them, okay? Now, the human body's doing that right now. You're making urea as we speak. But the big issue was that he was able to do it without a living organism and by taking what are considered to be inorganic compounds and creating something that is organic, okay? So there's another synthesis of it also that is based on an inorganic compound, okay, to form urea. So this is kind of where we credit organic chemistry for starting, but it's a little fuzzy in the rule book. Now, today, the big deal is natural products. This really started with a guy named R.B. Woodward, who was at Harvard. And he was the first person to actually synthesize cholesterol in a laboratory, tetracycline, the very well-known antibiotic, okay, and did a lot of work for making incredibly huge complex molecules that it just wasn't believed could be synthesized in a lab, and he did them in a laboratory setting. Okay, now, as we go through all of this today, we are going to keep writing the letter R. And R is kind of our variable. It's like in an algebra class. R can be anything organic. It might be as simple as 1 carbon long, or it could be thousands of carbons long. It's just going to be a variable, okay? All right, so there's some flashcards in your future. We're going to have to look at what we call the organic functional groups. We will start with alkane. Alkanes are straight chain carbons with every hydrogen they can possibly have. They will take the form of CX, H2X plus 2. Examples like CH4 and C2H6. Those are alkanes, okay? Pretty much all organics contain an alkane backbone. Now, alkenes all have double bonds at some place, and maybe more than one double bond. So the little variation is with an alkane, everything has single bonds, but with the alkene, there's at least one double bond present. With an alkyne, there's at least one triple bond present. And then we have alcohols. R with an OH group that is bonded to it covalently. We had OH groups back previously that were bonded to metals, and it was an ionic bond, and that made those bases, okay? But in this case, what we're dealing with is a covalent bond to a carbon, so that makes that an alcohol rather than a base. All right, so let's go on to page number 2 now of this outline and look at a few more functional groups, okay? We are going to start the page with what we call an ether, okay? So I'm going to get that straightened out for you. An ether is created from an alcohol. What happens is you take the hydrogen off of the OH group for the alcohol and you put on another R group. So R, oxygen, R prime. Now, R and R prime might be the same, they might be different. Okay? That it just depends upon how it was synthesized. Alkyl halides are an R with a halogen attached. We'll call that X. X can equal fluorine, chlorine, bromine, iodine. Okay? Amines have an R group with an NH2 attached. Okay? So, the next few all contain something that we call a carbonyl bonds. Okay? Carbonyl, or some people might pronounce carbonyl, is not a functional group on its own. Okay? It's just the name of a type of bond. Carbon double bonded to an oxygen. Now for an aldehyde, the carbonyl bond is at the end of the chain. And for a ketone, it's somewhere in the middle of the chain. Okay? So what we end up seeing is called a terminal carbon in the aldehyde. Terminal meaning it's at the end. And for a ketone, it's somewhere in the middle. Okay? Now for a carboxylic acid, you have an OH group that is attached to that carbonyl carbon. The carbon with the double bond of the oxygen is often called the carbonyl carbon. Esters end up having the hydrogen from the carboxylic acid replaced with another R group. Might be the same, might be different. Okay? Now, an amide has an NH2 group placed on that carbonyl carbon. Okay? Those are very prevalent in proteins. Thiols have a sulfur hydrogen group on the end. Okay? So those were the ones that had the carbonyl bonds, and now we are on to some that are slightly different. Aromatics. Aromatics are based on ring structures. And nitriles all have a carbon which is going to be triple bonded onto a nitrogen. Okay, there's a good handout on the webpage and that we'll pass out in class that shows you all of these structures. That's pages 1 and 2 of the outline. Thanks for tuning in. This is Morgan signing off.